Hello, everybody. Nice to see you all. This talk is called 10 to the Ninth. It's about performance techniques in a program I work on called Jepsen. My name is Kyle Kingsbury. You might know me as Aphyr at Woof.group. I go by he, him, and my day job consists mostly of doing distributed systems testing and safety analysis. I also do a little bit of teaching. This talk is about Jepsen, but I'm hoping that it will be generally applicable. In particular, Jepsen is a distributed systems testing framework, but it's actually really a single node Clojure program. It lives all on one machine. And it is reasonably concurrent, typically tens to thousands of threads. It also tends to be CPU and memory intensive, which means that I spend a lot of my life trying to make it faster because I have to sit there and wait for it to complete. And the more operations per second I can do, the more chances I have to find concurrency errors and bugs. So for the last couple of years, I've been doing a lot of performance work kind of in the background. I haven't been publishing as much. And this talk is kind of the culmination of that work. It's a bit of a grab bag. I want to go through all kinds of neat stuff, from functional things like persistent and lazy data structures, references to immutable values, some of the magic of Clojure's macro system. But we're also going to touch on some esoteric JVM things, like what does it mean to think about the layout of things in memory and minimize pointer chasing? What's up with executors? Can we have compiler at runtime generate classes for us to go faster? And we'll also deal with some sort of practical everyday questions about data structures, bit sets, on disk formats, and working with caches. All right, so with that in mind, this is not a JVM Performance 101 talk. That's a different problem. But I want to give a very quick nod to the general approach to performance work, which is you write the simple and correct code first. Only when it's too slow do you go ahead and optimize. In general, I want a profile with some kind of representative workload. That means something that looks like the actual problem I'm solving. If I'm optimizing a particular piece of the program, then I will design a test just for that thing. But I always want to know the context in the workload, because sometimes something might be expensive in isolation, but cheap compared to the overall work. For micro-optimization, I use Criterion, which is an excellent JVM benchmarking library for Java, and for Clojure specifically. My profiler is typically YourKit, but I've also used Visual VM and Java Mission Control. I tend to go for the easy, low-hanging optimizations first. That's usually type hints if I'm doing any kind of interop. Clojure level tweaks like changing lazy map to like a map with a vector a little bit faster to construct. Reducing the use of apply, for example. If the data structures I'm using aren't fast enough, I'll swap in Biverkin, which is a data structure library I'll talk about in this talk. Then I'll make fundamental changes to the shape of the code, new algorithms, new data structures, maybe introducing auxiliary caches. For things that are really expensive and frequently accessed, I'll go to primitives, actual int, actual long, and arrays. And I might write a little bit of Java. Those of you who are adventurous may be down in the realm of messing around with Java's unsafe namespaces, maybe FFI, maybe you're carving sigils into your JVM to summon the spirit of Cliff Click to intercede on your behalf with the scheduler. That is outside the scope of our talk. So I want to introduce a little bit of stuff about Jepsen first, just so you understand why these optimizations exist, and then we'll get into the fun part. As I mentioned, Jepsen is a single JVM program. It's just a Clojure binary. It runs the line again. It talks to a bunch of database nodes, and it SSHs to them and performs operations on them, and then observes the results. As far as the interoperation with the database nodes is concerned, it's all through clients. A client in Jepsen's world is like something that takes abstract operations and then performs some kind of network operation and returns a result. And those abstract operations could be maps. For example, this is an invocation by process number 3, which is performing a write, setting value x to 5. It is the 35th thing in the history, that is the index, and here's a timestamp in nanoseconds. This is a map representation of an invocation. The client could complete it, returning an OK operation with a new index and new time, typically the same f value. So every logical thing we do in Jepsen is represented as a pair of these operation maps. And these things are happening concurrently, multiple clients at the same time performing operations. So if time here flows left to right, we've got the top client that performs an invoke and completes. Currently, the client in the middle is invoking something and fails. Concurrently, the bottom client invokes and times out or has some indeterminate failure. When that happens, we log an informational operation in the log, but logically, that process is running forever. It will never terminate because we've given up on finding out what happens. In this case, we leave it running for all time, and we might spin up a new process logically to replace it. So Jepsen operates with a fixed number of worker threads, but a variable number of processes executed by them. The process is just a logical marker that does one thing at a time. In an abstract sense, the generator in Jepsen produces invocations, those operations we talked about. Those invocations go into the history, and then they are given to a client, which applies it to the database, returns a result, and constructs a completion operation with type OK, info, or fail. And that completion operation then goes into the history. So the history is just an append-only vector of invocations and completions updated concurrently by all these clients. From that, we can recover the consistency and concurrency properties of the system in question. We have a checker, which is just a function that looks at the history and tells us, was it valid? Did I find some bugs? And if so, what were they? So there's two phases, running the test and then checking the results of the history. Those two things have different sort of concurrency and performance characteristics. I want to talk about generators first. Generators initially in Jepsen were a concurrent mutable data structure. So you would ask for an operation from a generator, you would pass it a test map, and then which process your particular thread was executing at the moment, and you would hand you back an invocation operation, and as a side effect, it would mutate the generator. Under the hood, this used a lot of atoms and locks and things like that. But if you think about it, one of the most important things for a scheduler or generator operations to do is to control timing. And so you often have operations which would sleep for say 3 seconds and then call some other generator or return a map. And then you start asking, can I interrupt them? For instance, if I wanted to mix slow and fast operations, one that sleeps for 1,000 seconds and one that sleeps for 3 seconds, I don't want to delay the 3-second ones while I'm waiting for the 1,000-second one. And so I need to be able to bail out of certain paths and alternate. Also, you can be interrupted in your interrupt exception handler, and you could be interrupted in that thing's exception handler. Down this path lies madness. So after probably months of trying to make the system work correctly, I gave up and declared, fine, I will write it in a slow but correct functional manner. So the functional generators are pure objects. You ask for an operation from a generator, you pass it a test map, and some context that includes what all the threads are doing right now. And it gives you back a pair of the operation and our new generator state, which is what would happen if you did consume that operation. This is an effect system. If you've ever seen things like F, you turn all of your side effects into pure data structures, and then you have a little core of the system that executes the mutable operations over time. So we have an interpreter that takes the generator and just keeps it as a local variable in some sort of tight loop. It also keeps track of the history. The interpreter pulls an invocation and generator pair out of the generator and says, great, I'm going to log that invocation. I'll take the generator and update it with the new generator state. And then I will pass the invocation over to a worker via a single element wide queue. The worker then picks up that operation, hands it to its client, invokes it. The client does the work, it completes, and the worker puts it onto another queue, which goes back into the interpreter. This should look a lot like a message passing system, something a little bit like Erlang's actor model. The queues then hand that state back into the interpreter, which goes into the history. So now we don't need any synchronization on generator history because they're owned only by a single thread. The only points of concurrent handoff are these queues. Almost all of them are never contended for writes on the worker side. They're never contended for reads on the interpreter side. So this is actually pretty fast. Not super fast, but we're talking, hundreds of thousands, maybe a million operations per second tops. Now, one of the things that we need to do in this world is to manipulate these context maps, which keep track of the set of all threads that are available to run anything, the set which are free, the ones that are currently not executing something, and a mapping of threads to process identifiers so you can generate the appropriate operations. But these context maps are often changed as we go down a generator's tree. For instance, I can glue two different generators, one for reads and one for writes, into a new generator. which reserves the first two threads for reads and the next three threads for writes. And when I ask writes for an operation, I'm going to give it a context that is limited to only threads 2, 3, and 4. Now I can run different parts of the test on different nodes, or I can run several independent copies concurrently, but I need to do a lot of restriction. And the naive way to do that is to take the map of context, pull out the free threads from it, filter it to just those matching some predicate on the thread identifiers, and then turn it into a set. This is exactly what was in Jepsen before. As it turns out, this is super slow. This is actually 90% of our CPU time in fast workloads. Because if you have 1,000 threads, you have to call that filtering function on every single one of those threads. So you're going into an invoke virtual and coming back, and every one of them, because the hash set predicate requires hashing and then jumping through an array and then doing an equality comparison. And then you construct a bunch of seeks for the filter, and you unconstruct those seek wrappers, and you put them into a set which requires hashing again and resizing. And oh my gosh, and you do all of this 50,000 times a second. That's absurd. So you start asking, well, how do I make this faster? And one of my favorite tricks for performance is to observe that if you've got a fixed collection of things, you can usually give them numbers, and those numbers are often a lot more compact to represent. So let's take the thread set, which is typically a couple of named threads, like the nemesis that injects failures, and then a bunch of numeric threads, and let's make a translation table that maps back and forth between thread names, nemesis 0, 1, 2, 3, 4, and thread numbers 0, 1, 2, 3, 4, 5. And those numbers can be packed down into primitive integers. Now, physically, we build this table with an array of named threads that lets us go from number to name, a map of names back to numbers that we can go the other way, and then we just have an offset for the number of numeric threads, and it's just a matter of a little bit of mathematics to add and subtract the offsets appropriately to turn numeric threads into their corresponding numbers. So this is quick. Most of this is constant or like log 32n. Now I can replace my context map with one that takes advantage of these more compact representations. So I keep a copy of the translation table, and I also keep a process to thread mapping and a thread to process mapping. Because the thread IDs are now integers, I can store that thread to process mapping in an array instead of having to store it in a map. I can also store the all threads and free threads sets as bit sets, which means I can pack 8 distinct values into a single byte. So now I can pack a reasonably large number of items in a set into a really compact memory representation. And even though I have to rewrite the entire bit set every single time, it's so much smaller than the representation of an array set or a hash set that it actually works out to be faster. Now, some of this data never changes. The translation table, static for the entire test. The process to thread mappings, those change only when a process crashes. So they're pretty infrequent. But the all threads and free threads, those things get changed several times for every single call as you restrict the context down in the tree. And the good news is that those are now bit sets, which is pretty efficient to manipulate. In particular, that operation I talked about earlier, where we filtered the set of free threads using some predicate function, we know every possible input to this function. It's the set of free threads. And that implies that we could memoize the function. You're thinking, oh, Clojure has a memoize. No, we're not going to do that. We're actually going to call the function with every single possible thread, and we'll compute yes or no. And then we'll take those and we'll map them through the translation table and turn them into bit set indices, where 1 means that the input passed the function, and 0 means that the input did not pass the function. We've now compiled our function into a bit set of its possible inputs. And because that bit set representation is exactly the same as the representation of the free threads and the all threads map, we can just filter them by doing bitwise and, which is something that CPUs are really quick at. Sort of things easily vectorizable. So the cost of this function went from materializing all of these seeks and having to do traversal and hashing into just a pair of bitwise and operations and a little bit of memory copying. It becomes essentially free. With 1,024 threads, we get a 10 times speed up in the overall throughput of the test. Not just the generator context part, but the entire generator assembly. Went from about 2,600 operations per second to 26,000 per second. So I count that as a win. Next fun thing I'm working on is disk streaming. Test maps in Jepsen have some metadata, things like a name, the start of the time that we did the test, history, which is a big vector of operations, and then the results, which is typically a map that's also pretty chunky. And at the end of the test, we would write that entire map with all of its components into a freshened file on disk. It's a serialization format. And for reasonably large tests, that took like 10 minutes. You're just sitting there waiting, like, okay, I know you've got a memory, but I can't look at it yet because it still has to go to disk. And then when you load it, the REPL, you have to wait another 10 minutes for it to come back. And also, it's really heavy in memory. It would be great if this stuff were incrementally written to disk during the test, so I didn't have to like wait at the end, and if I could read it piece by piece. So I've made a file format. This will look familiar to anybody who's done protocol or file design before. You put a magic string at the front, in this case Jepsen, a version number so you can interpret the rest of the file, and then there's a mutable 8-byte index offset into the file. This tells us where to start reading. The rest of the file is an append-only log of blocks, where every block has a header of a length, checksum, and type, and then arbitrary bytes. The checksum is computed incrementally, so you can stream a block, and then only at the end do you checksum the length once it's known, and then the type fields. So with that, we can start building index structures. The index block provides a mapping of block identifiers to the offset in the file where they're found. Why have block identifiers instead of using offsets directly? Well, this means that if I have some big data structure written in the file that has a bunch of references to like block 42, if I want to change block 42, I can just write a new block and then write an index block that has a new mapping for block 42, and I don't have to go and rewrite the entire other file. I can leave the references in place and then mutate only the indirection table. So again, we're separating values and references to gain a little bit of efficiency. I can also represent data structures as partial maps. So if I have a big test map like results or tests, I could store just a few fields in a map inline and then have a pointer to a block that contains the rest of the data. Now, if I want to ask if a test is valid, it's super fast to parse. But if I want to find out the rest of the test's results, for example, dive into why it was invalid, well, then I would go to the rest block ID number 4. I would parse that and then merge those results back into the uplight map. So now I can build lazy maps, which are fast to access certain fields and slower to access the bigger ones. I do the same thing for tests. So the Jepsen file contains a history, a bunch of stuff, and at the very end, it has an index which points to the root node, which is the test itself. The test then has a pointer to a history and a pointer to the results. Those things can be lazily decoded, so I only need to read as much of the file as is actually necessary to show what I'm asking for. As a result, load time, which used to be linear, maybe upwards of 10 minutes for some big files, is now about a constant 25 milliseconds. That's to load a handful of small top-level blocks. That's a great transition. I love this. I can do interactive work with REPL now. I could also have a web interface that opens all the files and shows me, pass, fail, what were the names, what were the variables, what were the timestamps. Parsing that stuff is cheap enough that I can do it and show an entire page of results without having to wait. For the histories, I wanted to write them in a streaming fashion, but I also wanted to be able to recover from crashes. So if I killed the test halfway through, I might have 3 hours of data I could still analyze. I'd like to be able to pick that up and start working on it. So I want a system which can recover, and for that, I'm gonna have my streaming data written to a freshen block piece by piece. And then once I finish a block, say 16,000 operations, I will complete it and I'll write a new index that includes it. And then I'll start the next block. And then if at any point I crash, my index pointer will always point to a point in time consistent snapshot of the file. This is what gets me sort of atomicity, even though I'm incrementally writing. Then I can stitch together all of those stream blocks into a single vector. So I store a big vector block that has the count, the number of elements that are in the vector, and then a table of integer offsets into the vector, and then which block ID contains them. So if I want index 3 from this vector, I'm going to look at offset 0 and offset 16,384 and say it's between those two. I need to go to offset 0's corresponding ID, which is 3. That is the fresh and stream block that contains my entry. So I do a little bit of logarithmic scanning just to binary search my way through the right offset. And I jump to that part of the file, decode it, and read it. I get constant time reduce, constant overhead on count, and logarithmic time n. And all this can be represented just as arrays in memory. Under the hood, I'm going to back those array chunks, the actual pieces of the vector that I decode, with a soft reference. And soft references are a JVM thing that will reclaim memory if there's memory pressure. So the garbage collector starts to go, oh, I'm really full. It'll erase a few soft references for you. This means that I can represent a vector that's much, much bigger than memory, but the pieces that I'm actively working with will be retained, and I will keep as much of them as I can until memory starts to become an issue. It's a memory adaptive cache. But it looks just like a vector. So the overall test structure now becomes this incremental append-only log with a persistent shared structure tree encoded in it. The header tells you the index is the last block in the file. The index tells you the test map is just before that. The test map points to the history and to the results, which are stored again in a tiered series of maps. The history has a vector that points to a bunch of operation chunks. Now I can decode all of this structure as I need it. I get crash recoverability. I have a bounded time, about 50 milliseconds, to decode any chunk of the history. So if I want to look at just the first few operations, it's really cheap. It behaves exactly the same as a regular map, as a regular vector. You can associate onto it. All of the existing code works as is. And if you update it, we store pointers in the metadata that let you write it back to disk, and it will reuse the existing on-disk pointers to unchanged structure. Also, there's a garbage collector. Next thing I want to talk about, data structures. We need them. We need a lot of them. Most of my time is spent manipulating enormous maps or sets or vectors or things. And for that, I'd like to use Zach Talman's Bifurcan library. It's a family of Java data structures, which are written a lot like Clojure's persistent and transient vectors and sets and maps. So you can have a version which is clobbered in place and really efficient to append things to. And then you can seal it and get a version which has efficient shared structure copying. They come with extensive generative tests for correctness and performance tests. And one of the neat things about this is that the performance is often within an order of magnitude and sometimes even faster than the Java stock collections. But they're functional. And they've got an expanded API. I can, for example, ask for the nth element of a set or map. That turns out to be really handy for doing random sampling. I can find the closest thing that's just above or just below some index in a sorted collection. I can also efficiently split and merge. So I can do like set union, set intersection, map union intersection, splitting apart a list into chunks. Those things have efficient bulk optimized functions inside of Bifurcan. So I found that replacing code that uses Clojure data structures with Bifurcan can usually buy me a factor of 2 to 10 times faster, oftentimes more compact in memory as well. If you want a Clojure wrapper, you're in luck. I wrote one just last week. It's called Aphyr/Bifurcan CLJ. I've been using this for a few years, but haven't bothered to release it yet. When it comes time to traverse over data structures, I often wind up writing reductions, like a lot of reductions. I will reduce over all the things in the history. And then for each operation, I will have a transaction stored in its value. So I'll iterate over that with another reduce. And maybe the values themselves are lists of elements. So I will reduce over that. So I know what reduce function, reduce function, reduce function. This nested insanity, trying to thread multiple layers of state in and out of those things. Every single iteration is structuring and destructuring vectors, which puts a ton of pressure on the garbage collector. So if I'm doing all of this iteration through histories, I want a better way to do it. I have terrible news. I finally broke down, I wrote a macro. It's called loopr. This is a hybrid of loop and reduce. Like loop, it starts off with initial bindings for iteration. So I'm going to start off with a sum and a count of 0, and these can be primitives if you like. Then I'm going to have a for style binding iterator. So I say for every x in the collection 1, 2, 3, And if I wanted to, I could do additional layers of iteration on top of that with the Cartesian product. Then, like loop, I have a recursive expression. So if I put recur in any tail form, it will go back to the start of the loop with new bindings for sum and count. So here we're going to find the sum of items and the count of items in a single pass over the data. The fourth thing is a final form, and this is evaluated when the iteration is complete. You often want to build up intermediate structures, like for this mean, we're going to keep track of sum and count separately. But what I care about is their division. Or maybe I'm going to build up a transient data structure and I'm going to call persistent the last time. When you're doing this with reduce, you have to wrap the whole thing into a level and then do some destructuring on the accumulator. It's just a lot more convenient to put it in line. So I'd say about 90, maybe 95% of my iteration has this shape, and I've wound up using loopr from almost all of it. Why? Well, it compiles directly to the equivalent reduce or loop constructs using either iterators or array get. And it has heuristics that actually generally pick the fastest way to iterate. And if I need to change that, I don't have to rewrite all of my code. It's the exact same shape. I can just hint, hey, traverse this thing using an array. It supports early return using either reduced or loop termination. I get type hinted accumulators, and I can do multi-dimensional iteration, which is kind of a pain with plain old reduce. And all of this is anywhere from 2 to 10 times faster than the idiomatic equivalents in loop or reduce, depending on the type of variables you're working with, the dimensionality of the reduction, and the accumulators you have. Why? Well, it turns out that reduce spends an awful lot of its time just pulling apart vectors or maps. Every single time you do a reduction step, you have to call a function. You pass it a vector, and you split it into 3 parts, and you make another vector and glue them back together, and you do it again and again and again. We can get rid of that. Loops over collections tend to do a seek, right? You start off with seek, and you do first, next, first, next. That's a whole bunch of garbage collection pressure. Reduction is a lot faster. In a similar mode, there's a macro called reducer that I use a lot. And this thing takes the exact same form. I have a sum and a count. These are the initial bindings for accumulators. I then have an iterator variable, x. And then I have a recursive body. If I don't include a recur, that's an early return. If I do, it just keeps recurring. And then I have a final form at the end. This thing returns a function that will work with reduce, transduce, Clojure core reducers fold, all of those things. The single arity generates an accumulator. The two arity form combines the accumulator with an element, and the single arity form turns the accumulator into some sort of final result. But here's the twist. The accumulators and the code that it generates for combining all work with an instance of a dynamically compiled Java structure, which has primitive mutable fields for the accumulators you want it to use. So instead of having to pull apart a vector, we're actually going to reuse the same element every single time, which reduces GC pressure and improves cache locality. And we're just going to bash its fields in place. We're going to set its primitive long copy of the sum and the primitive long copy of the count and just increment them as they are. That turns out to be way faster for multi-accumulator reductions. If you want to use these things, you'll find them in DOM-top, which is my library for control flow for closures with masochistic sensibilities. Talk about histories. Histories used to represent operations as plain old Clojure maps, which is great. You should start off everything with maps. The problem is that maps internally, whether array maps or hash maps, are a whole bunch of object references. All of the keys on the left here are references to objects that live elsewhere on the heap, and all the values are references to objects that live elsewhere on the heap. The only things that are stored in line are the null pointer. And so if I want to find out what the, say, time is of this operation, I have to scan through all of the keys doing keyword comparison. Thankfully, that can be done in reference. And then I look at the reference that goes to the corresponding value, and then I have to go to memory and pull that address in, which burns up a cache line. And then I have to pull apart the long that wraps the value. And so there's additional unboxing there. So Clojure has a great solution for this. They're called records. I do a def record for Jepsen operation, and now instead of having explicit encodings of the keys, they're implicit. I just have fields in an object for the process type f and so on. Access to them now compiles into an offset lookup in that instance. And the primitive values can be pulled in line. So index and time, which I use all the time, Those puppies are now represented as primitive longs inside of the object. Great. So I've improved memory locality. I've improved the amount of memory I use. I've made it faster to do keyword access. Now I want to talk about the representation of the history itself. What does it look like to have a vector of these things? And originally it was just a vector. That works fine up until maybe 1 to 10 million elements, and then it starts to really get creaky. So I said already that we're going to represent histories as soft references to lazily parsed data that's read out of chunks in this disk file. But I'm going to wrap that in an additional Jepsen iHistory type. There's a few implementations for sparse or dense histories. And that thing has some superpowers. In particular, I often want to take a history and just look at one little part of it in time, or maybe just the history on a single node or a single process. That gives me a history whose indices, instead of going 0, 1, 2, 3, go 5, 8, 7, sorry, 5, 8, 9, 10. They're going to be sparse, might be gaps, might be offsets. If I want to look something up by index, I will keep an auxiliary integer map, which is compiled lazily, and that will let me look up the efficient index, turning it into essentially a logarithmic time operation. I also need to go back and forth between invocations and completions so I can understand the concurrency structure of the test. When did I actually start asking for this thing? What was going on then? I can build a single primitive long array which maps index to index so I can jump back and forth now. And that lookup time is constant. Again, I can build this thing lazily on demand. I can build it concurrently, having each thread pass over its own little chunk of the data and then merging the arrays together. And I just keep that thing built into the history so access is fast when it's needed. This used to be a data structure that every checker would individually build and keep a copy of. And so you wound up building 20 copies of the same map and having to do map lookups all the time, which is a good deal more expensive than an array. Another huge cost in Jepsen was filtering and mapping over histories. There's a lot of places where I did a naive filter or naive map, and that's fine until you start getting really big. And then it starts to weigh you down. In particular, filter gives you a lazy seek, which I believe is 32 element chunks at a time. And if you want to iterate over it, you're going to be materializing seek pointers into that seek. So you have a lot of garbage allocation. And if you wrap several stages of filters, you're doing wrappers on wrappers on wrappers. It creates a lot of garbage pressure. Now, the canonical Clojure answer is to use transducers here, but then you have to pass around two things, the history and also the like partially built transducing function, and then you would glue on additional transducing functions later. Now I have to have two arguments instead of one, and I have to keep track of both things. And it would just be much nicer if I had a single object that meant the history only on this node. So if you call history filter and you give it a predicate and history, it gives you back a new history object which retains a reference to the old one, again preserving all of its lazy disk access. It keeps a memoized count and a memoized mapping of indices for efficient lookup. And then it pushes down the filter operations to only when you actually ask for it. So it's still lazy. If I ask for the 15th item, it'll grab the 15th item from the underlying collection, and then it will filter it and make sure. And if that doesn't work, it'll keep iterating until it gets the right index offset. Same thing for reduction, same thing for count. Identically for map, now we have efficient maps which are compact. And all of these things are verified to work just like their vector equivalents with generative tests. Makes a test.check. One of the other superpowers of new histories is that you can fold over them. Histories support reduce, just like vectors do. The way it's implemented is to construct an initial object, the accumulator. You reduce over the first chunk, and then you could, if you wanted to, let the garbage collector eat it. You parse the second chunk and you reduce over that. You parse the third chunk, you reduce over that. And you go all the way through the chunks until you've completed. And then you call the function one more time to post reduce. That's what, say, turns transients into persistence. This is exactly equivalent to a straightforward vector reduction. It's just that we're doing it incrementally, so we don't have to materialize the entire vector in memory at any time. But more than that, we can do concurrent folds. I could do that reduction in parallel on every chunk. So one thread grabs chunk 3, parses it, reduces over it, while the neighboring thread grabs chunk 4 and parses that and reduces over it. We do that independently. lots of threads, I can go faster. Then I have a serial combine phase, which glues together the results of all of those chunk reductions. I call that combine. So it starts off with an initial state, we combine the reduced value, we combine that reduced value, and then we do a final post-combine, again, to turn transients into persistence. This is the same idea behind MapReduce, which look really familiar if you've ever heard of that paper. It's also inside of the Tesser library for composable commutative folds. And it turns out that Tesser's representation of maps is basically the same as Jepsen folds. Jepsen folds has a few extra powers. Uh, if you want, you can use Tesser to compose these folds and then pass them right into the history, and they will work just like you expect, including if you do more than one at once. We have multi-query optimization, kind of like a database. If you want to do two folds at the same time over the same history, for example, finding the minimum and maximum elements, if there's nothing that stops me from having min and max and gluing them together into a new reducing function. To build an accumulator, I make an array of the minimum accumulator and maximum accumulator. To merge in an element, I would call the minimum function with the minimums accumulator and the element, and the maximum function with the maximum accumulator and the element. And then to seal, I would seal each piece individually. And I could repeat this up to, 40 or so folds, however many I want. I just put them in an array. And now I get improved memory locality. Right now, a single thread pulls in an element, and it can do all of the operations on that particular element, rather than each separate CPU core having to pull that element in and doing them in different places. This is a lot more cache efficient. So if I have a thread that's trying to perform a fold of a min over the history, it might have spawned, say, two initial reduced tasks on two chunks. The way that we do this in Jepsen is you start off with a single reduction, and when that finishes, we actually spawn two more, and then four more, and eight more. So they kind of ramp up their concurrency over time. And the reason is, if you're going to spawn a whole bunch of reductions really fast, like a second person tries to do a fold with maximum, well, there's an optimization. We know that we have to do separate reductions for the ones that the minimum fold is already doing. But for the second chunk, and for every chunk that hasn't been touched yet, we can do a single pass over that data and compute both min and max in that one pass. And then we can stitch together those things in the combined phase that nobody notices that we actually did some parts independently and some parts concurrently. So if I spawn, say, 40 or 50 reductions, which is common for Jepsen, a lot of checkers doing lots of passes, it will efficiently do as much of that work in a single pass as possible. That minimizes the number of times we have to reparse data. We don't have to throw things away anymore. We can reuse the filter and map stages I talked about. Those things are applied once, and then we can fork after that. We can improve cache locality because we're always streaming the same data through the same processor as opposed to having to replicate it to multiple ones. It's friendly to the prefetcher since all of our access patterns are linear. And it's all done in a way that's mutability safe. Your accumulators, even though they're being shuffled and split among multiple threads and forked and joined, we guarantee that you don't have to do any locks. You can clobber state in place in your accumulator, and it will just work correctly. Again, validated by concurrent generative testing. Practically speaking, reducing with 10 folds on a 24 physical core, 48-way box over 10 million JSON operations on disk, I see about an 80x performance improvement versus the sort of traditional, linear reductions. So these techniques combined can buy us a huge improvement in real-world performance. To do that, I needed a transactional version of a thread pool executor. And if you've ever worked with executors, you know that they're actually kind of a pain. In particular, you often need to pass work from one task to another. So maybe I would block on the completion of the other task and use a future or promise there's something to hand off data between them. But if you do that, the thread that's blocking chews up that thread. It can't do anything else, can't be released. And so the executor gets stuck. To some extent, virtual threads are hopefully going to fix this by spawning endless virtual threads and letting the blocking IO deschedule them. But if you're looking at traditional thread pool executors, starvation is a real issue. Also, we need to guarantee that we can atomically add and cancel multiple tasks at a time. I need to be able to cancel both phases of a reduction that are pending and replace them with a single unified pass. And if I didn't do it atomically, if I killed something that was actually in progress, I would violate that mutability safety property I talked about. I need to make sure that I never attempt to start a reduction and then have to cancel it later. So atomicity is impossible with traditional executors. There's no way to do it. You could end up canceling a task that's already starting to run. So thinking logically, if I have a graph of tasks I want to perform, like I want to eventually feed the dog, but to do that, I need to first take the dog for a walk and I need to get food at the grocery store. And I can't go to the grocery store until I visit the bank. I'm going to make this first class in the executor. I'm actually going to have a graph of tasks represented in the executor itself. In fact, the executor queue is literally just this graph. So the sugar for this, and there's a functional version of the hood where you just pass in, function dependencies. But the sugar is that I call task, and it takes an executor and a friendly name so that I can debug it later, and a vector of dependency bindings, and then arbitrary code, just like a future. That code gets wrapped into the function, handed off to this executor, and it's executed only when all the dependencies are satisfied. This guarantees I never starve a thread. Everybody can make progress as long as you're cooperating inside of the dependency world. Obviously, you could block an external dependencies, and if you do that, that's your problem. If I want to depend on something else, well, I pass a binding vector. So here I'm going to find errors in the history, but before I can do that, I need to have the index task's results, and I'll bind that result to index. And then I can evaluate my code using the index variable in there, and this will only run when the index completes. All of this does error propagation, by the way. So if the index task throws an exception, that exception propagates down, cancels the downstream tasks, and they all pop up with the same exception, and the stack traces are preserved. I could dereference this just like a future. If I ask to deref a task, it blocks on the completion and returns the value of the body, or it will throw if the function threw an exception. I can cancel these tasks, and I guarantee a very specific safety property that's not a part of usual executors. I say that either T will finish or it will never start. This is important for that mutability safety. I want to make sure that I never have a thread start touching a mutable object and then have to give up and do it again. That would violate safety on the mutable structure. And I can do transactions. I represent that graph I talked about and all of the executor state as a pure immutable structure. And then I can do a swap style function where I say, hey, do a transaction executor, or do a transaction on the executor. Here's a function of your executor state. And now I have pure versions of cancel and submit and so forth, which return a new state or a state in a task. So I can evolve that state doing several operations. I can add all my new schedules, all the pending reductions I need. I can cancel the ones that aren't going to happen. And I'm guaranteed all that takes place at a single logical time. So to recap, all of this work has bought us anywhere from 1 to 2 orders of magnitude speed up in request rate and checking, and that's on overall sort of real world throughput. We've gone from linear time memory overhead to constant memory overhead, usually just a few hundred megabytes during the course of a test, instead of blowing out a 16 gig keys in an hour. We've gone from linear time to load a test to constant time, usually just a handful of milliseconds. Analyses routinely use 70 to 90% of a 48-way machine. Jepsen 027, doing a listed pen test and testing for G1A, aborted reads, and G1B, intermediate reads, would top out at 7,000 transactions per second, and it was limited specifically by the generator. It would blow out a 16 gig heap in about an hour and a half by writing just 25 million operations, and then it would just run out of memory and give up. That would produce 1.9 gigabytes on disk, and if you wanted to analyze it, you needed a 58 gigabyte heap. Lots of reasons why materializing that data back into RAM got really expensive. Jepsen 033 tops out in this particular workload at 11,200 transactions per second. The bottleneck is no longer Jepsen, it's the database. The actual generator is more than capable of going to 50,000 a second and above. That same 16 gig heap, no problem running indefinitely. We can do a billion operations, 10 to the ninth. It takes about 26 hours to get there at that rate. Produces 128 or 108 gigabytes on disk, and we can check it in just a few gigabytes of heap thanks to that adaptive self-reference caching system. And the whole thing is highly concurrent. List append will top out now at about 50,000 operations per second for actually testing. checking, which is the full deserializing the operations from list append test and doing like a trivial count, that pushes about 900,000 operations per second now. And this is on a box built in 2013, so I assume modern CPUs are probably faster. We could get to 1 billion operations and above for histories. At some point, I'm going to have to start breaking the JVM collection assumptions because they think that everything's in terms of integer indices, and that's not going to be big enough anymore. All right. I want to say thank you in particular to Justin Conklin, who contributed some code for Clojure.asm inside of Don Talk, and also to Zach Tellman, whose libraries and thought continues to inspire me. In particular, his Potemkin library, which I use extensively for def interface and for gluing together inheritance, and also the Bifurcan family of data structures, which I cannot emphasize enough for basically every Java programmer or JVM person at all. Like, it's phenomenal. They're such a game changer. I love this library so much. Thank you all for having me. It's nice to see you. If you want to learn more about this research, you can go to jepsen.io, and there's a blog post that's a companion to this talk at aphyr.com. That's all.